Welcome back to my physics class. In today's lesson, we are going to learn about acceleration. Acceleration is a change in velocity divided by the change in time, or the equation A is equal to delta V over delta T. As I mentioned in the previous video, equation 2 and equation 3 in your formula chart are the same equation, but just isolated for different variables. As we start one-dimensional or 1D kinematics, you will see small letters below your variables. These are subscripts that identify exactly what the variable is referring to. For example, the subscript of F and I next to V refer to final and initial velocity, respectively. In short, acceleration is the rate at which velocity changes over time. Just like velocity, acceleration is a vector quantity and will have positive and negative values. Unlike velocity, the unit for acceleration is meters per second squared, compared to meters per second for velocity. In on-level physics, we are primarily concerned with uniform or constant acceleration, which is an acceleration that does not change. One of the biggest examples of constant acceleration that we will work with throughout the year is acceleration due to gravity, or AG. Because gravity pulls everything in a downward direction, the value of acceleration due to gravity is negative 9.8 meters per second squared. The value of AG is one of the very few things that you are asked to memorize in this class, and will never be mentioned or referred to in a problem. Therefore, it is your responsibility to recognize when acceleration due to gravity is involved in the problem, and for you to remember and use the negative 9.8 meters per second squared value. A positive acceleration can mean increasing velocity in the positive direction or decreasing velocity in the negative direction. A negative acceleration can mean decreasing velocity in the positive direction or increasing velocity in the negative direction. Sounds a bit confusing? Don't worry. Let's hope this chart helps clarify it a bit more. The easy way to remember this, and I suggest writing it down, is that when an object is speeding up, the acceleration is in the same direction as the velocity. Likewise, when an object is slowing down, the acceleration is in the opposite direction as the velocity. Let's move on to some sample problems. In 1954, Colonel Stopp did a variety of tests for the military to determine the limits of human body under extreme acceleration. In one rocket sled test, he went from 1,020 kilometers per hour to rest in a small time of 1.4 seconds. What acceleration did he experience as he came to a stop? In this problem, the question is asking us to find the acceleration that Colonel Stopp experienced. One of the most common mistakes that students make is that they select negative 9.8 meters per second squared for any question asking about acceleration. Keep in mind that negative 9.8 meters per second squared is the acceleration due to gravity and only affects vertical motion and movements. In this problem, the movement is horizontal, and AG does not affect horizontal velocity. We will discuss this in detail at a later time, but for now, let's focus on solving this 1D horizontal problem. First, let's look at the problem a bit closer. As we take a look, we only have two numerical values of 1,020 kilometers per hour and 1.4 seconds. However, there are certain keywords that give us additional clues and values. The word from indicates initial, and the word to indicates final. The words rest and stop both indicate a velocity value of 0 meters per second. Now that we have taken care of that, let's list the unknowns and known variables. Our unknown variable is acceleration, or A, with the units of meters per second squared, and our known variables are time, or t equals 1.4 seconds, vi, or initial velocity of 1,020 kilometers per hour, and vf, or final velocity of 0 meters per second. As you may have noticed, the units for vf and vi don't match, and we have to convert our initial velocity from 1,020 kilometers per hour to meters per second. I've shown two different methods in which you can convert kilometers per hour into meters per second. Either way works just fine. Next, we have to decide which equation we will use. Since our known and unknown variables are t, vf, vi, and a, we can use either equation 2 or 3. I've shown both equations to simply show the math steps used for algebra review purposes, but as you can see, the answer is the same. One of the most common mistakes is that students often mix up final velocity and initial velocity values in the equation. This is why it helps to list your variables early on and refer to them as you substitute your values in the equation. I hope this lesson has been helpful. Don't forget to hit like and subscribe, and have a wonderful day.